We're now going into the different kinds of transport proteins now. The simplest type, the simplest type of proteins are going to be gates. Gates are what they sound like. Some of them are always open. So these leak gates or leak channels are simply an opening. If you have a fence and there's one little gate in it, what that means is that's where things can come and go. If you have dogs in your backyard and you have a gate, they can't get out through the fence, but they can get out through the gate. Now, put more gates, they can get out more frequently. Put one gate, they won't get out as often, especially if you have a stupid dog who doesn't remember where the gate is. But they are simply open all the time and will allow things to pass through them anytime they find the gate. Remember, we're talking about molecules. Molecules don't have a brain. They don't remember, oh yeah, that's that thing down to the left somewhere. They literally float around and bounce off the membrane until they find the actual little channel and they can go through. That is by far the simplest. It's literally like just sticking a straw right through something. And if you find the straw, you can travel through. You also have ones that are gated, which means they can open and close. If they can open and close, that means you have some control of whether you're permitting things to go in and out. Leak proteins, leakage channels are always open. They always allow things to flow through them. Gated channels are going to have a valve to them that you can open and close. And in some cases, those things will be open and closed by some sort of trigger molecule. A ligand is a fancy word for, well, if we go back to here, in the most generic terms, that's a ligand. A ligand is a thing that binds to a receptor protein. Yes, within that monstrous category, I mean, neurotransmitters in your brain are ligands because they simply are things that attach to a molecule and make something happen. In this case, this is a gate that you need a key for. The key happens to be those little yellow ones right there. And when those yellow ones stick, the gate opens and then the little pink ones can go through. So the one thing about these is that things can only go with the gradient. And that's what we're about to talk about on this next page. Gradients are enormously important. Your entire nervous system functions on gradients. What we're talking about is differences on one side of the membrane compared to the other. So something that's different about what's going on the inside of the cell versus the outside, something about what is there. So there's more of one thing outside than inside. There's more of something different inside than outside. The idea is you probably memorize that diffusion is movement of a molecule from high to low concentration. The direction of high to low is referred to as a gradient. So if you look at this first picture here, those potassium ions, the little triangles, the gradient, the concentration gradient of potassium is in this direction. That's because there are more inside, there are fewer outside. They want to go from when there's more to where there's less. And so the direction they naturally want to flow in this example is out. At the same time, there's also a gradient of the Sodium. The sodium wants to come in because there's more of them outside than there is inside. And so you can have multiple concentration gradients at once. You're going to refer to it as the concentration gradient of potassium, the concentration gradient of sodium, of oxygen, of you name it. Very, very, very rarely are things in equal amounts inside and outside of a membrane. In fact, you will find, you may run across this like sort of statement in other parts during the course, but equilibrium equals death. If your cells ever have equal amounts of stuff inside and outside, like everything, every molecule that's inside the cell is in exactly the same concentration outside, that's because you're dead. That's the only time that ever happens. Think about it this way. For your body, which is the concentration gradient of oxygen, into you or out of you? Well, into you. There's way more oxygen around you. There's way less inside you, and it wants to simply diffuse into you. Yes, you have to suck it into your lungs, but from there, it just passes from the air in your lungs straight into your bloodstream because that's the concentration gradient. Where's there more carbon dioxide? Inside you. So when you exhale, you don't exhale oxygen, you exhale carbon dioxide because it wants to leave you. But when you exhale less oxygen than you sucked in because it wanted to go in. There's a concentration gradient of everything. If you ever get to the point where the concentration of oxygen is the same outside you as inside you, it's because you're dead. Okay, so concentration gradient, purely concentration gradient, is simply based on molecules. We don't care what they are. Yes, we care that they're different. The sodium has its own gradient. The oxygen has its gradient. The potassium has its gradient. They don't care about each other. The fact that the potassium wants to come in has nothing to do with which way the sodium wants to go. Totally separate. There can also be an electrical gradient where there are more positively charged things on one side of the membrane compared to the other. You can have like more positively charged ions on one side and fewer positively charged ones on the other side, and you end up with a difference in electrical charge. Typically, that doesn't happen by itself because since ions, electrically charged atoms, are the only thing in you that could create electrical differences, it means that for you to have an electrical gradient, you have to have uneven numbers of electrical molecules on one side of your membranes or the other. So we don't usually refer to anything as just being an electrical gradient, because if you've got a concentration gradient of electrical things, of ions, what you have is an electrochemical gradient. Now, if we look at this picture, you can see that I'm going to draw in some little pluses and minuses here. So potassium, plus, 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 and then sodiums, those are pluses. Down here, plus, 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 plus. So if we count all of these up, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 positively charged things outside, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 positively charged things inside. That is an electrochemical gradient. So the outside in this thing is a plus 11 charge, and the inside is a plus 10 charge. You have a charge difference, and that charge difference is because there are chemical gradients of things that have charges. You will beat this into oblivion in your brain when we do the nervous system, because this is the reason why nerve messages exist, is that you have these electrochemical gradients in nerve cells that you intentionally create so that they can carry messages. That's the electrical activity of your brain, is electrochemical gradients. Okay, so when things move, super generically, you have two types of transport: free and not free. Passive means it doesn't require energy. It will just happen. The only types of passive diffusion are these three. Diffusion, which is movement of any molecule from high to low concentration. Osmosis, which is the movement of just water from high to low concentration. And facilitated diffusion is diffusion from high to low. Passive transport, any diffusion or osmosis, is always high to low concentration. Things can't roll uphill. They can't roll from where there's more. They can't roll from where there are fewer to where there's more. Things don't want to do that. If you put ink into water, it spreads out. It does not ever want to come back together into a drop again. It never does that. That would be going against the gradient. The only things realistically those three things are the only things that actually diffuse through that lipid bilayer of your cells, through the membrane. Every other molecule that wants to come in or out of the cell, even if there's a concentration gradient where it wants to come in, the problem is they can't squeeze through the membrane. The membrane is too tightly packed, and so they need doorways. You know, your house, there are some things that can penetrate the walls. I guess in theory, oxygen or something. But for big things like you need doors, right? You don't just morph through the walls. So almost everything is going to happen that's passive is almost always going to be facilitated diffusion, because you need a door for the stuff to move from high to low concentration. And remember, sometimes those doors, gates, can open and close, right? And so it's movement of things from high to low concentration. They never, ever can go from low to high. Things go the way they want to. Things flow in the direction they want to. If you want to make things go where they don't want to go, if you want to shove molecules to a place where they don't want to go, you are going to have to do active transport. It needs energy, but this lets you pump things against the gradient, pump things uphill. It's going to require energy the whole time, but you can do it. So simple diffusion, just things spread out. And in this case, they're using, I don't know, green salt. There you go. The thing with simple diffusion is it's free. But for the cell can't control what happens. So for example, what I mean by can't be controlled is if things are diffusing out of the cell, it can close a gate and make it stop, but it can't make things diffuse in that want to leave. The cell look, if something's going to be free, you got to take what you get. What you get in nature is moving from high to low concentration. If that is not the direction that the cell wants, and that's going to kill the cell, oh well, you can't make it go backwards for free. There are factors that affect how fast it happens, but they're not factors that the cell can control. They're just factors of nature. So first, it's basically how steep is the concentration gradient. If you've got that many things outside the cell and that many things inside the cell, they want to move in. However, if you've got that, they still want to diffuse in, but they're going to diffuse in a lot faster. Basically, you'll see on an upcoming picture, I've got a picture of one of these, a water jug. If that sucker is filled all the way to the top, that liquid is going to flow out of that spout pretty fast. But as the water level drops, it flows out slower and slower and slower because there's not as big of a difference between the level inside and the level outside. So that's what I'm talking about with, like, the bigger the difference, the more full it is on one side than the other, the faster it's going to rush in the direction of high to low concentration. Second, little molecules move faster. They just do. They zip around faster. They can squeeze through tinier openings, and they will just move quicker. So small molecules like oxygen diffuse much faster than big molecules like sugar. And then finally, temperature. If your body is warmer, things will diffuse faster because warmer things have molecules wiggling around faster. And so warm molecules will wiggle their way from high to low concentration faster than really cold molecules that are moving super slow. Like literally at the molecule level, that's all cold is. Cold means molecules that don't have enough energy to move very fast. So cold cells, cold situations make things go slower, which is why when your fingers are freezing cold, you can barely move them because the chemical reactions that you need to make your fingers move are happening so slowly, which is why you're fumbling with your keys when your fingers are like frozen because they barely are working because nothing's happening fast enough. But those are all factors of the environment. The cell can't control any of these. You're at the mercy of high to low concentration. So some things can squeeze through the membrane. So these are the three that I always talk about. Yes, there are very specific kinds of things, like, for example, cholesterol-based hormones like estrogen. Those can pass right through the membrane because this center section is the part of the plasma membrane that's made out of lipids. It is mostly fat, and molecules made of fat can pass through there fairly easily. However, molecules that are not made of fat, so the term for this center section is hydrophobic. And then the very inner and outer surfaces are the opposite, water-loving, hydrophilic. So because the vast majority of the thickness of the membrane is water hating, other water hating molecules can slip through, but water loving molecules cannot. Most like water soluble things cannot just go through the cell membrane. They need a doorway. They need to use one of these channels. The other things that can't go through are ions. Sodium, potassium, hydrogen, chloride. Even though they are super tiny, they have an electrical charge. And that center section of the membrane, the hydrophobic region, hates electrical charges. It repels them. Positive, negative, it doesn't care. So very, very few ions can pass through the cell membrane. You will see as we go, that's an incredibly important thing because that's why your nerves work. That's why muscles work. You'll see all of the ions being used as like triggers for stuff. But aside from carbon dioxide, water, oxygen, and lipid solid molecules, everything else that's going to diffuse into or out of the cell needs a channel. So carbon dioxide, water, oxygen, and those can go right through the membrane. Everything else, molecules that are not lipid soluble, molecules that are big, molecules that are ions, none of them can go through the membrane, and they need channels, which means if you don't have a channel for something, even if it's in high concentration outside, it's not going to go in because it can't. It has no doors. Or if you have channels that are gated and you close them, yeah, the stuff wants to diffuse in one way or the other, but it can't because no door. Now, osmosis is the very specific situation of the diffusion of water. It gets its own name because of how common it is and how uncontrollable it is for cells. You are going to see an example of this in a little while, but basically water also wants to go from high to low concentration. Duh, a sponge. You take a dry sponge, put it in water. The water soaks into it. Take a wet sponge, put it on the counter. It will start to leak because the water wants to now flow out of it. Right? It's a natural process. You cannot dry a sponge out by throwing it in water. Can't do it. Water does not want to go out of the sponge when it's a dry sponge that you just threw into water. Won't happen. So water always wants to spread out so that the amount of it in one place and another is equal. If you noticed, you're kind of wet inside and it's going to dry out here. That means water constantly is wanting to diffuse out of you by osmosis. That's what happens when you have a burn victim who has lost a big area of skin, because your skin is waterproof. It holds the juiciness in. If you lose your skin, you literally will start to like have water evaporating out of you faster than an IV can put it in. Somebody with severe 3rd-degree burns, dehydration is one of the biggest risks, that and infection. So there are a ton of situations where the amount of water in you is regulating other things. You're going to see all kinds of examples of this, and I'm going to show you a few specific examples in a little bit. But just remember, osmosis is just the diffusion of water. Oh, aquaporins are water channels. Yes, water soaks through the cell membrane. But if you wanted to soak through faster, poke it full of holes. Water flows through a colander faster than it flows through a coffee filter because there are more big openings for it. And so if you want water to flow through faster, poke it full of little holes. That's what aquaporins are. They are water channels through the membrane that basically make the cell membrane super leaky to water.